Thank you, Quincy, and I want to say it's really a great pleasure to be here. Thanks to the University of Auckland for inviting me, and also for New Zealand Society of Earthquake Engineering for hosting the lectureship. This is the second time I've been to New Zealand. I was here last year, and I went to the conference, and I have trouble saying the town Rotorua. I think something close to that, approximately. And it was a great experience, so I'm really happy to be back. The talk is about self-centering, and I'll use the words many times during the talk, so I won't dwell on this slide anymore. I'll move forward, but it is about looking at higher mode response in addition to the basic rocking behavior. And I've sort of had a lot of collaborators over the years in this area, as well as a large number of sponsors. Some have been industry sponsors, in particular in the steel industry and the precast industry. Colleagues, Rickles and Pisecki especially, Professor Liu, who's no longer with us at Lehigh, and two more recent colleagues, Professors Fleischman and Restrepo, and a large number of PhD students. So those are the people who really did all of the work. And as I mentioned to Quincy, I have this slide which says a little bit about the center. It's Advanced Technology for Large Structural Systems, and it's a so-called Engineering Research Center, which means it was created by our National Science Foundation a long time ago to try to be a collaborative institution to bring people together from different disciplines. And the ATLSS stands for Advanced Technology for Large Structural Systems. One of our main features is our laboratory, and it's, I guess, similar in size to the Newmarket laboratory here, probably a little bit smaller. It's been there for about 30 years, and we have a lot of equipment and a very talented staff. And what makes it, I think, special is our ability to do lots of large-scale tests. For example, this right here is about half the width of the Bronx-Whitestone Bridge in New York City, about half the width of the actual bridge in our laboratory at full scale. So that's the kind of thing that we typically pride ourselves on. So here's a sort of a summary or introduction of the talk. And I think there's quite a bit of experience and knowledge about self-centering systems here, so I'm not going to spend too much time on the motivation. I have a few slides about that. Talk about some work we did on steel systems, and then talk about really what to do about the higher mode response. And I'll make that a little more clear as the time, as we get there, including how to quantify it and also how to engineer for it. So let's talk a little bit about the motivation. In the US, and I think it's fairly similar around the world these days, we designed for something we call life safety, which is actually a little difficult to define, in fact. And we designed for something called a design basis earthquake, which is about roughly 500-year return period earthquake, ground motion. And we don't explicitly design for either immediate occupancy under more frequent earthquakes or collapse under maximum considered earthquake, but we expect to get that kind of performance by designing in this way. And one of the results, which I think the Christchurch experience bears out as well, is that we can expect a lot of damage to occur under ground motions that are fairly intense, but not necessarily the maximum considered ground motion. And that can have some serious economic and social consequences. So in the US, there's a push to think about this differently, as I'm sure there are in places that had other recent earthquake experiences. And so we need to think about how we can get to this low damage condition in a reasonable way. And that's really the main topic for today. So this is a couple slides that show the kind of damage we might expect in something like a 500-year return period. Here's a post-Northridge, so this is the improved beam column connection design in the US, and we see local buckling and some yielding, some damage. This is a kind of buckled braces we might expect under a 500-year return period earthquake or something like that. So if we think about self-centering systems, we really want to think about doing this in a different way. And this is some points. I think these are sort of the main points. I have a few more on the other slide about what we're trying to achieve, why we're doing it this way. The first thing we want to do is eliminate damage to the main structural members, and yet we know the structure still needs to be deformed. It's of course always possible to take a structure and design it to be linear elastic. In fact, there's even one building that went through the Northridge earthquake, hospital building, Silmar Hospital, that actually was almost linear elastic, and it had accelerations at the roof of about 2.5 G. And so everything else in the building got damaged, although the structure wasn't damaged. So there's different ways to make the structure undamaged, but typically we need to provide some kind of softening mechanism. And we'd like to do that in this case without having damage to the main structural members. And so we do that with some kind of post-tensioning, Here's an example of a beam column joint. Here's a rocking steel braced frame. The post-tensioning closes those joints, which open up under the earthquake loading, and we avoid any permanent lateral drift. And I said I don't think this idea is necessarily new in New Zealand or to this audience. Some of the early work we did was was going back to the mid-1990s in the so-called PRESS program. And the PRESS program was a Precast seismic structural system program. And in the US, it wasn't possible to build precast construction in a seismic zone before this work was done. And even today, there's still some challenges in getting permission from the building authorities to do that. In that particular program, the work that we did at Lehigh was to study walls and frame systems. And for the wall systems, we were able to show that you can get pretty large drift capacity, in this case 3.5% drift, with essentially no damage or very little damage to the wall. And so that opened up a possibility of surviving the design basis earthquake with essentially little or no structural damage. Another thing we learned in this particular stage, is very early on in the work, was that we get a lot of deformation capacity without really depending too much on material ductility. So here was a wall that went to 6% drift that we couldn't fail. You see it always self-centered as well, but it was impossible to fail within the laboratory capabilities we had. We had 3 cycles at 6% drift, and that was really without exhausting the material ductility. So that's the kind of thing that we learned at that point in time. Of course, there's a lot of other work that was done, and here's 2 examples. Some work at UCSD on their shake table. Sorry, I wasn't on their shake table. In their large lab, it was a pseudo dynamic test, and that you can find that in the PCI journal. And also some work by Restrepo and Raman on a hybrid wall system. So other important work was done in this area. We at Lehigh decided to look more at steel frames at that time, about 1995, 6, 7 or so. And we looked at that as a response to the damage to the steel Northridge, the steel frames in the Northridge earthquake. And those were essentially conventional welded moment frames that suffered fractures and other kinds of serious deformation and caused a lot of economic distress to the owners of those buildings. And so we looked at developing a self-centering steel moment-resisting frame during that time. And here's an example of one at 3% drift with essentially no structural damage at all. There's some challenges to that system, and so we haven't really done too much with it going forward. I'll show you a video in a minute or two that we did do some work, some experimental work. We kind of let this go for the time being. But what we learned from that is really this energy dissipation is a designable or an engineered feature of the system. So when I was a graduate student, a PhD student, we were taught that this kind of large hysteretic response was highly desirable, that was the goal, and our professors would get pretty excited when they saw that in the laboratory. And I look at it now and I just see damage. I see buckling, yielding, rebar yielding, cracking of concrete. I just see damage. So we found is that actually if you want that energy dissipation, you can do something else and fatten this hysteresis loop out or make it skinny or whatever you prefer to do. You can make it self-centered. You can get the same initial stiffness without doing anything extraordinary. So those are the kind of things we learned from that work. So about the mid-2000s at Lehigh, we thought we proposed to do something called damage-free steel frame systems. And I think we did this as a collaboration with some people at Purdue and Princeton. And I was the only one of the people who thought that we should use the word damage-free in the title of our proposal. Everyone else thought it would be the kiss of death, that we have no chance of success of getting it funded. And so we did it anyhow. We put this in the proposal, and I don't think we thought we would get there. But in fact, we did. And that's what I'll show you with the next maybe 6 or 10 slides or so. I'm going to show you first the MRF, and I'm sort of downplaying the MRF because at the end we have found that this is not perhaps the best system for us to go forward with. But the yellow frame in here is a 4-story moment frame, and what you can see here is a video which shows how it behaves. This is what we call a slow hybrid simulation. It's very slow unless I get it going. Which means it's a time-lapse video, and the test took about half a day to do. And what we can see is the gap opening response in the moment connections and the nice sort of flag-shaped hysteresis loops that people have come to expect. And at the end, we'll see that the roof drifts or the floor drifts come to basically zero, and the building is fully plumb afterwards. We use a little friction device in here on the web to dissipate the energy, and that's what gave us the width of these hysteresis loops. But at the end, we found that this is very difficult to make work with a reasonable floor system. And we actually had a floor system in this two-bay frame that simulated that response, and we showed that we could make it work, but it really wasn't very practical. So we've moved on, although they are built in the U.S. in precast concrete these days. Although I don't really understand how they deal with the floor system issue there. I don't think they do it very well. Our main focus here is on these rocking steel frames. And this is a concentrically braced frame. You can see the orange bracing here. So I get the pointer back. And these are our reduced scale undergraduate students here working in the laboratory. It's about 60% scale. And the yellow columns are what I'll call gravity columns, which actually don't rock or uplift, and the orange columns in here are the columns that will. And what we did early on in this, and this is, we started this work around 2005 or 2006, we worked numerically on different kinds of systems that would rock and try to find the sort of the appropriate or the ideal system for us to work with in the laboratory. And this is an example frame B, and ultimately we came up with something which we called frame D along that series of A through D. And it had columns which don't uplift, which we call gravity columns. It has concentrically braced frame columns which do uplift. And we thought the relative motion between those columns was an opportunity to dissipate some energy. With a little more study, we decided that we would use friction devices in that area. And so this is ultimately what we did in the laboratory. And this particular system is discussed in this paper from the World Conference. We have post-tensioning, which pulls the structure back down as it rocks and gives us some self-centering response. And as I said, all the energy dissipation is through these friction bearings, which this next slide shows in a little more detail. And there's the gravity column, which doesn't uplift, and there's the concentrically braced frame column, which does uplift. And in there's a bearing with a knuckle steel, hardened steel on a piece of brass in this case. And the way that force develops there is we have the floor system, which has the lateral forces in it, and the floor system pushes on the gravity column, and the gravity column then pushes on this bearing. And there's a cutout within the floor system which permits that rocking to occur freely. So in these self-centering rocking systems, we try to consider these two performance objectives. And I'm going to ultimately focus on the first one much more than the second one. And that's damage-free with potential for immediate occupancy under the design basis earthquake. And the main thing we want to do there is control the yielding limit states, really deciding when those limit states will occur and control, let's say, their sequence and the intensity of earthquake under which they occur. And collapse prevention, we actually show later on that we can get that. Actually, I don't know if I have the slides in this talk, but I have some slides that show we get good collapse prevention performance relative to conventional systems, but that's not really where I'm going to focus so much today. First is to think about the limit states of this rocking system. And the first limit state is actually rocking, and there's some range of behavior under which it won't rock, and that could be reserved, for example, wind loading or moderate earthquakes where we really don't want to initiate that nonlinear action. There's column decompression or uplift of this column here. Ultimately, some yielding of the PT steel. We use PT bars here, and we're not adverse to having those bars yield, although sometimes if you use strands, there's some concerns. And then later on, with more drift and higher intensity earthquakes, we can expect yielding or buckling of the members and maybe fracture and failure as well. So thinking about where we want those limit states to occur, there's a median level DBE response, and we want that to be perhaps around when the PT yielding occurs, maybe a little below. We recognize that there's some uncertainty in how much that demand will be, and we consider that a little bit later on. And then for the median MCE response, we think about this around maybe when the members begin to yield or buckle somewhere out there. So I won't spend a lot of time talking about this prototype structure. It's 4 stories. It's designed for a site in California. And we have, of course, some tributary seismic mass associated with each one of the brace frames. And I really want to focus more on what we did in the laboratory on this. So here's what it looked like in the laboratory. There's our PT anchorage in the roof level and down in the basement. These yellow columns, as I mentioned here, are going to stay anchor, they're not going to uplift, and the orange columns will, and there's a friction bearing in between there to take advantage of that relative motion. So in the hybrid simulations, these are all laboratory simulations. They're all slow, so no real-time stuff here. We did a large number of them. I'll mention in a minute, 31 simulations ultimately. Before that, we tried to get our bearings in terms of how intense the earthquakes needed to be. We did numerical response statistics for 30 ground motions, and you have like a mean value of the drift, about 0.9% for the DBE and about 1.5% for the maximum considered earthquake. And as I mentioned, we did 31 simulations in the laboratory with the same structure. And there aren't many structures, I think, that could survive 31 earthquake simulations at the design basis earthquake or the maximum considered earthquake. And I'll show you at the end that this structure performed really quite well. I'm going to show you two different ones from the set. One is this Arletta ground motion from the Northridge earthquake, and one is from Takatori from the Kobe, the 1995 Kobe earthquake. First, I'll show Arletta, and these are multiples of the standard deviation of the drift. So we're about 1.5% drift or 1.4% drift, and about 1.5 to 2 standard deviations above the mean. And here's the response that we would see. And this is again split screen showing the uplift of the columns and the lateral drift. And so this is about 60% scale, as I mentioned before, and so we're seeing perhaps 100 millimeters of uplift or 100 or something like that, maybe not quite that much. And that's it. That's a typical DBE response. Of course, we get the self-centering behavior because the PT pulls it back. The PT remains linear elastic. We get flag-shaped hysteresis loops that we're expecting. And so there's really nothing very spectacular about it. And I guess that's what you want. If you're looking for damage-free response under the design earthquake, you really want nothing to happen. So that's essentially what happened, nothing. So the other hybrid simulation I want to show you is the Takatori record. And this is a record which is specifically intense for this structure, as I'll show you a little bit later. It produces a drift of around 4%, which is 5 standard deviations above the mean. So it really is an extreme case, and we labeled it extreme MCE for this particular structure. And here's a video, and I'll probably play this twice because I think it's pretty interesting. And again, this is 60% scale. I guess we're seeing about maybe 200 millimeters of uplift or something, almost equivalent to the dimension of the column. And I'm going to play that one again because I find it entertaining myself. So again, this is actually time-lapse video, and this is, again, a slow hybrid simulation, so some of the dynamic effects might not be included in that. We can talk about that perhaps later. The roof drift still self-centers, and we have, as well, something that sort of looks flag-shaped in terms of the hysteresis loops. They start out flag-shaped, and then eventually, as I'll show you in a minute, we lose the post-tensioning, and so they become sort of very linear through zero. Here's the reason that record produces so much drift. We have a period of around 0.65 seconds or something like that, and the period elongates into this large area of energy within the spectra for that. So we're actually responding and seeing the response to all this energy out here in the 1 to 1.5 second range. And so it turns out to be a bad ground motion for that particular structure. This is the PT response, and as I mentioned, we use PT bars. We use duodag bars in these cases. And we can see the initial PT bar force, and then some increases in force. And eventually, we've yielded the bars so extensively right there that we lose all the PT force. And then the PT force picks up again as the structure continues to rock. And eventually, at the end, we end up with no force. And I don't have time to talk about that right now, but if there's questions about that later on, we are actually not so concerned about that kind of behavior. It's not something we want to happen under the design earthquake, but we don't think it represents a collapse potential for the maximum considered earthquake. So there's the frame after our test, 31 records, DB and MCE response, and no damage to the brace frame at all. And that's really kind of findings we have no damage under any DBE, essentially no damage under MCE. We did some damage to the load bearings because the load bearings had both large large deformation responses and large forces on them simultaneously. The PT bars yielded, but still performed well under even a post-MCE aftershock, and we did that in the laboratory. We also found that restressing the bars could return the structure back to its initial state. We never replaced the bars. We did 31 records, yielded sometimes. We never actually replaced the bars. We just restressed them. So I want to talk a little bit about design. And I think some of the ideas are generally useful for these self-centering rocking systems, but I'm going to focus on the SC CBF because that's where we have our experience base. But I imagine some of the ideas would also work for other systems. And as I mentioned earlier, we have these two really performance objectives. One is damage-free under the design earthquake, and one is collapse prevention under the MCE. And I'm going to focus really on the first one. And as I mentioned earlier, we find that we get this one without really putting a lot of effort into it. And really the first one is the challenge. And I'll focus again on application to self-centering concentrically braced frame buildings. To do that, to get that damage-free performance, we actually have two issues to address. One is when the PT bars or when the PT steel will yield. And that's essentially what I would call a first mode response. It's essentially the dominant mode, dominant response. And I think really most shear wall structures or structures that can develop a flexural mechanism have the same characteristic, that's really a first mode response. But the local design forces, the things we have to engineer for to keep the members from yielding or buckling is actually a higher mode issue. And so they're almost two, not almost, they are really two separate issues, and I'm going to address them separately. The first one is really focusing on the PT yielding. And in these performance objectives, we think a lot about what the consequences are. And say the consequences of minor PT yielding are small. It's concentrated damage. We know where to find it. It's in the PT steel. If we have to replace the PT steel, it's all in one place. If we don't have to replace the PT steel, we can just restress it. It's a fairly straightforward operation. So the consequences of PT yielding, we think, are relatively small. So we have proposed to design the PT for a 50% probability of PT yielding under the DBE. We find that even when it yields, it doesn't yield much, and we don't lose a lot of the pre-stress necessarily. In the Takatory record, we lost it all, but that's an unusual response. So that's the kind of the idea. We're going to design for this median response. And really, to get there, it's really not that difficult. First, we have to make an estimate of our DBE level drift. And we do that by having some idea of the drift at decompression, this first instance of nonlinearity, using some kind of ductility factor, project forward, and come up with an estimate of the DBE response. And we found that we actually get pretty good estimates this way. And it's not that difficult to make a good estimate of the drift demand under the DBE for this system. As far as the capacity, we just recognize there's two kinds of deformation capacities. There's an elastic capacity that's present without the rocking behavior, and then there's another part which is due to rigid body rocking of the frame. If you have enough rigid body rocking, eventually you'll yield the PT, so it's not that hard to figure out when PT yields under the rocking action. And so here's a quick example of how we handle that. And I said I don't think it's that challenging to understand how to do it. Sometimes the detailed calculations might be challenging, but the concepts are pretty straightforward. We have an expected response under the DBE. We could decide to factor it if we wanted to provide more margin against yielding. We have a capacity we can calculate pretty easily. And at the end, we've decided that we're going to not factor that up. We're going to have a gamma of 1, and we're just going to take this capacity and push it down, if need be, down very close to the DBE demand, and not worry about it more than that. And we have quite a bit of experience with the performance of structures that are designed this way from numerical simulations, and this gives us pretty good response. Now, the more challenging one is how to design the members for a low probability of yielding, considering the higher mode force response. And there's a couple points here which are important. One is the force response is not controlled by first mode rocking. So all the forces in the braces and the columns, all the things that we're concerned about, trying to keep them from yielding and buckling, are not really a first mode response. They're a higher mode response. The consequences are potentially serious because it's distributed all over the frame. So if you buckle some braces, it's a multi-story frame, you have many repair actions to take. So we want to have a fairly low probability of that occurring. And I think maybe foolishly, we selected a very low probability, 5 to 10%, which means that we ended up designing for very high forces. But that's the kind of design that you saw in the tests that we showed earlier, that very low probability of member yielding and buckling under the DBE. So we're actually trying to find forces which are way out here in the tail of the possible member force response. And so this led us, and this is really a question we asked ourselves really a bunch of years ago, how do we quantify the higher mode force response if we want to somehow control it? And we came across this idea of effective pseudo-acceleration, and it's in the papers, it's kind of a footnote in the papers, but I wanted to spend a little more time today to talk about that because we found recently that this was a much more generally useful device, tool, way to quantify higher mode response. And so we've used it in a number of different ways recently. So this is a little bit of a sort of review of some of the ideas related to pseudo-acceleration. And it's so natural for us as earthquake engineers to use this quantity. I think sometimes it's not always clear exactly what we're doing. We're just kind of using it in the way we always have. And so we think that we have an equation of motion for a multi-degree of freedom structure. We know we have a restoring force. Often people write that as K times displacement, but I want to generalize it for nonlinear structures, so I just write it as the restoring force. In linear dynamics, we think of the restoring force as being a summation of something called S, and this is from Chopra's book. These are static forces multiplied by a pseudo-acceleration response, which is time varying. Really, we can write the response of any force response in the structure in terms of static quantity times the pseudo-acceleration. And typically, in our practice, we're getting the pseudo-acceleration from single-degree of freedom systems. And we're calculating that, and we're going in this way. We're calculating this restoring force from that. And for design, we can use the peak pseudo-acceleration to basically estimate any response, mode by mode. And then we, of course, have to have some mode combination approach, which we'll leave till later. We'll get to that in a little bit. So what we're doing here is we're using the same idea for nonlinear structures. And of course, we can't do the forward approach I just showed. We can't go from pseudo-acceleration towards restoring force. We actually have to think about it in an inverse way. And that's how we ultimately can understand how to quantify the nonlinear response. So just as a thinking, first of all, from the design of nonlinear structures, typically what we're doing is we're taking that pseudo-acceleration for a single degree of freedom system and dividing it by a response reduction factor or behavior factor. We use R. In the US, you might use R. What do you use in New Zealand? RD? Yeah. In Europe code, I think they use Q, but everyone's doing the same thing. We're dividing by this. And we're thinking of this as a nonlinear pseudo-acceleration. I don't think it is actually the nonlinear pseudo-acceleration. I think it's our best guess in a really simple way of calculating it, but I don't think it actually is. Here, what we're going to do is we're going to calculate from the restoring force the effective pseudo-acceleration. We're going to go in the opposite direction. And we start out by thinking of the restoring force time history as consisting of modal components, and ultimately taking the static force quantity and expressing it as multiplied by what we call the effective pseudo-acceleration to get those nonlinear modal quantities. And so by decomposition, we can solve the problem inversely. So this pseudo-acceleration quantity here we call the effective pseudo-acceleration, and that's actually the thing you could use to quantify the response in each mode for a nonlinear structure without introducing any errors or any approximations. Okay, all it requires is the mass orthogonality of the modes. And that's what this shows here. So we use this equation, but essentially we're solving it inversely, and we're using that as the effective pseudo-acceleration to quantify the response. Another way to think about it is you can think of the restoring forces consisting of some vectors multiplied by some unknown quantities, which we solve for. And these are sort of well-known force quantities here. So of interest for us is actually the nonlinear response we might use in design. And we're going to say that's a static response multiplied by some peak effective pseudo-acceleration for a nonlinear structure. So I'm going to give you a couple examples to show you what we can do with this quantity and how it can be compared against other kind of pseudo-acceleration type quantities. So it is a very simple structure that was prepared by one of my PhD students. It's a numerical model shown there. It forms a plastic hinge at the base. It has this bilinear elastic plastic behavior. So it's very simple, subjected to a whole set of ground motions, and calculated the effective pseudo-acceleration initially as a time history for each mode, and then found its peak values and plotted the peak values. And here's a result that people have often shown where we can see that by having this nonlinear response, we're affecting the first mode and not really affecting the higher mode. But here's another, perhaps a more dramatic and direct comparison of that idea. So there was all the effective pseudo-accelerations for the second mode and the third mode. There's their median value. And we can see they're kind of very close to the elastic single degree of freedom response. But for the first mode, it's actually quite a bit lower. It's almost, but not quite, down to the level of the spectral acceleration divided by R. So we're almost seeing the first mode being controlled by the plastic hinge at the base of the structure, but not exactly. But that's a pretty clear evidence of how the first mode is controlled by the yielding mechanism, how the higher modes are not. In fact, we see a tremendous amount of scatter there. And we can take the same approach and look at structures which are different numbers of stories, 4 stories, 12 stories, structures designed with low R values, so almost elastic designs, or structures designed with high R values. We basically always see the same trend, that the higher modes are typically essentially linear elastic, and the first mode is being controlled by the plastic hinge forming at the base. Again, I don't think any of this is particularly new, but it's just a different way of showing it, perhaps, a more clear way of showing it. Now, we also can do this with other mode shapes, and we call these alternate mode shapes. And this concept was used by Sullivan et al. In 2008 in a paper they wrote, and they called them transitory inelastic mode shapes. But these are basically shapes which are centered around a certain yielding mechanism. In this case, for this particular simple structure, it's a plastic hinge forming at the base of the structure. And so we can make mode shapes which are based on that as opposed to the elastic mode shapes, and we get a little more clear picture of what's happening in the structure. So these are a plot comparing the mode shapes. These are the elastic mode shapes in black, and these so-called mechanism mode shapes in blue, which are based fundamentally on this being our first mode. And we see the mode shapes are quite similar to each other in shape, but these mechanism mode shapes have a very interesting characteristic in that at the base, they have no moment. They produce no static moment. So this mode shape is a mode shape such that actually, if I use that as my fundamental basis, I have one mode shape which is directly tied to the plastic hinge at the base of the structure, and all the other mode shapes are actually completely independent of the plastic hinge that forms at the base of the structure. And that allows me to get a much more clear picture now, using this, again, effective pseudo-acceleration, of how the yielding at the base of the structure controls the response. So with these mechanism mode shapes, what I have here is I see almost perfect control over the first mode response. And what I see is actually I'm exactly right at my spectral acceleration divided by R, which is what I designed it for. And the higher modes are still uncontrolled by the base hinge mechanism. Okay? The other thing that we can see clearly with these other mode shapes is we can actually see the yielding mechanism form. And so I look at the time history of the effective pseudo-acceleration and see right here, that's when the yielding at the base of the structure occurs. And that actually is now a very clear picture of how, at that point in time, my first mode response is controlled by the yielding at the base of the structure. So this is the idea we want to use. We want to use this effective pseudo-acceleration now to figure out how to design our SC CBF for the higher mode response. And so that will be the term. That will be the term we use to quantify the higher mode response. So come back to our problem. And our problem was, how do we get these low probability of exceedance member forces for design? And so we're going to contrast this with a conventional response spectrum analysis, at least how we do it in the US, if we're going to design a code, trying to design a building according to code using response spectrum analysis. And as I think is typical around the world, we typically divide the entire spectrum by R, and that means our higher modes are being designed as if we had controlled them somehow by the nonlinear mechanism that was forming. And I just showed you that, in fact, that's not true. Here is the higher modes that we would design for in that case. And for the kind of response spectrum analysis that we're proposing for these self-centering concentrically braced frames, we do reduce the first mode based on the yielding capacity of our base mechanism, our rocking mechanism. But in fact, for the higher modes, we end up scaling them up. And this gives us really good performance, but also creates, I think, some expense that we want to, of course, be paying attention to as well. Here's a picture of actually the data that was being used by Brent Chancellor, who's a PhD student who did this work. And what he shows is that here's our design spectrum, which is this black line, first mode, second mode, third mode, and so on. This is the data from his nonlinear analysis results. That bar there is the median response, and so the median response is quite close to the design spectrum. We take that elastic response and scale it down, essentially using an R factor or some kind of modification, response modification. And we take the higher modes and scale them up by some factor we call gamma. And that gamma is actually pretty large, 1.6. So here's the kind of, I guess, the simple answer to that question. If you want to design so the members don't yield or buckle, with only 5% probability of yielding or buckling in a design earthquake, you have to take your design spectrum and scale it up by 1.6, not divide by R. You have to go up instead of down. And that, of course, leads to some pretty big design forces. Okay? So this is what we did, and that's how we got the performance that you saw in our test results. So here's a summary of that. You take your first mode pseudo-acceleration, you actually scale it down based on the PT yielding capacity. You take that and you perhaps scale it up a little bit to give us some margin a margin against the first mode response. Use an unreduced pseudo-acceleration to design spectrum, and you scale that up by 1.6 to get the capacity we want. Use a modal combination procedure developed specifically for these buildings. So one of the things I didn't talk about was modal combination procedure in design. And I'm going to only have a couple slides to talk about that. One of the things that we were able to do with the effective pseudo-acceleration in a very useful way was actually study the correlation between modal responses. And here are the classical results. The SRSS that people use, or CQC. CQC based on some work that Karagian did based on random vibrations of linear elastic structures. And we found that none of that was particularly useful. That actually the correlation between the first mode and the higher modes actually varies depending on what response quantity you care about. So if you care about braces or you care about columns, it's quite different. And so here's some examples of the peak shear in various stories of a 9-story concentrically braced frame. And the correlation could be -30 or -40 or -0.05, different results. If I look at the peak moment versus the peak shear in the same story, it could be 95%. So there's quite a bit of difference in correlation between various response quantities at various locations in the structure. And so the CQC or the SRSS methods can't actually give you that kind of result. But if you use the effective pseudo-acceleration, look carefully at the correlations among the modes at the times of these peak responses, you can observe it. And so Brent Chancellor kind of tried to boil that all down to something quite simple. And he found that if you use 2 sets of correlation coefficients, you could get a pretty good bound on the kind of forces he might get in the members. So here's a summary of that. And this is really just sort of on our design approach. You know, we allow that PT yielding to occur. It's really a drift-based approach. We use a modified RSA with load factors to get a low probability of member yielding. And we have to really develop a special modal correlation approach to get really the right result at the end. And we need the effective pseudo-acceleration both to estimate those load factors, gamma, and also to get the modal combinations. So the cost of this performance, I really wouldn't try to quantify, but you get some strange results I'll kind of explain later with another figure. The column sizes in these concentrically braced frames, as we tried to design them to say up to 18 stories, became really large. And that's because the member design demands are really large. This whole idea of designing for a very low probability of response in these higher modes with these gamma factors led to really extremely large design forces and then large members coming out of that. So that kind of caused us to think about this in a little different way. And we could see that we had done a good job of controlling the first mode response by rocking, but we really had uncontrolled higher mode response. And as the earthquakes got bigger, the ground motions got bigger, the higher mode response got bigger. So this is a good example of what you get from that. Here's the bending moment, or the story moment up the height of the structure. And you see as we go up the structure, the moment's actually bigger than it is at the base. And that amount, it's bigger than it is at the base, would even be greater if I used a larger ground motion. So as the ground motion became more intense, that bulge becomes even bigger. So this is really because we're not doing anything to control the higher mode response in these rocking structures. So we'd like to mitigate that somehow, and so we started looking at some different approaches. And I have 2 approaches. One is really focused mainly on how to sort of control the second mode alone through adding a second yielding or rocking mechanism. This idea has been developed already by others, Panagiotou and Restrepo and Wiebe and Christopoulos. So there's that idea, and then I have another idea I'll present a little bit later on, which is sort of heading in a different direction than this. So by using the effective pseudo-acceleration, we're able to do things with this approach that others were not able to do so far. And that is to sort of make a direct correlation between the response in the first and the second mode and the strength of these plastic hinges or rocking joints, if they're rocking joints. We sort of directly relate them to the first and the second mode responses with some equations here. I won't go into the details of that. So by doing that, we're actually able to really provide a predictable reduction in the effective pseudo-acceleration for the second mode. So we could actually say, well, here's where the second mode response will be if we design that second hinge to have a certain strength. Put it right down to a specific value. Also recognizing that, of course, we're getting the same first mode control that we're getting previously. So this is a tool to get the second mode to be as well controlled as the first mode with a second hinge. We're able to create some, if you will, bounds or envelopes on what the first and second mode response together could be. So bounding that combined response, either in terms of shear or moment up the height of the structure as shown here. And then try to see how that compares to nonlinear dynamic analysis results. And that's what this figure shows. So it's a little hard to see, unfortunately, because these two things are overlapping each other. There's these two responses here. One is our envelope. It's our kind of our predicted maximum combined first and second mode response in terms of moment up the height of the structure. And underneath that is actually the dynamic analysis result of the actual absolute upper bound moment for all the ground motions in the ground motion set up the height of the structure. And they're really essentially identical. So we have sort of a perfect bound from this calculation involving this envelope. So if we know the peak effective pseudo-accelerations, we can actually get a perfect bound. But also, and the same thing for the shear of the height of the structure. But this slide shows that really when it comes to sort of coming up with an extreme value, say 2 sigma, so median plus 2 standard deviations for the moment up the height of the structure, or median plus 2 standard deviations of the shear in each story, we don't do a very good job of that because now the third mode response is there. And so you're chasing this problem, right? So first we're controlling the first mode with rocking, great. Now we can control the second mode by introducing a second mechanism, great. Now the third mode is there. And of course, as the structures get taller, these higher modes will continue to be an issue. So I think if we can bound that, we can come up with a way to sort of say, well, here's the maximum force we have to design. And we certainly can see that we've pulled this in a little bit compared to what it would be without this second mechanism. But really, at the end of the day, we've sort of taken it one step at a time. And it's really a work in progress, but we have ways to estimate that upper bound response in terms of moment or shear, and we've developed some better methods for that. But it's really a work in progress, and at the end, I don't know that we're actually going to eliminate the problem of having to design for fairly large forces in order to get the performance that I showed you earlier. So one of the ways then to deal with these higher mode forces is to try to mitigate them by adding a second mechanism. The alternate approach is the use of some deformable connections between the floor system and the lateral force resisting system. And this is a collaborative work that we're doing with Jose Restrepo and Robert Fleischman at the University of Arizona and UCSD, as I show here. And this was actually presented last year at the New Zealand Society of Earthquake Engineering annual meeting by my PhD student, Georgios Sampras. So we'll show you a few slides from that talk, and then that'll be the conclusion for the talk. So, you know, for a conventional structural system, earthquake resistance system, we think we have basically 3 parts to that: a gravity load system, including some framing, whatnot, a floor system, and a lateral force resisting system. And we assume that the floor system is essentially rigidly connected to the lateral force resisting system, and that's our sort of conventional way of thinking about this. For this alternate approach, we put some cutouts in the floor system, and we try to create some separation, if you will, between the floor and the lateral force resisting system. We add a limited strength hysteretic component. In this case, it's shown as like a friction device, which is going to transfer the force into the lateral force resisting system. And we add some bearing components, which actually brace the lateral force resisting system in the out-of-plane direction. And then that would be the sort of total combined system. And the goals are to limit the force that we transfer to the lateral force resisting system and reduce the accelerations and responses. And this approach actually is remarkably effective. I don't know how practical it is in terms of construction, but it's remarkably effective, as I'll show you. It actually solves some of the problems of rocking structures in the sense of how to handle the upward motion and things like that. But I think it also poses a lot of practical challenges. But we'll show you the results we have. Interestingly enough, this idea, something like this, first appeared in a paper in 1975 by Skinner, Kelly, and Hein, where they were looking for sort of good ways to put hysteretic dampers into structures. And they thought by separating these 2 pieces apart, they could somehow find a good way to dissipate energy. We find it's useful at dissipating energy, but it's actually more useful at controlling the forces. There's a structure that we studied about 2.5 years ago at UCSD, and it's a precast rocking wall, shear wall structure. It's half scale, and it was tested on the shake table at UCSD. We use a friction device as our hysteretic force limiting element, and we use some rubber bearings between the shear wall and the floor system to brace the shear wall out of plane. And here's a video that shows that, and I might play this video twice because I think it's pretty interesting. There's a friction device doing its job and transmitting forces into the shear wall. You notice the structure has torsional response, and that's intentional. We actually designed the structure in an eccentric way so it would have a torsional response. And I think I'll play that again. The friction devices more or less did what we thought they would do. They transferred a very predictable level of force into the shear wall from the floor system. Okay. We also did some tests at Lehigh on this in a full-scale sense, and it's important to do these things at full scale because the forces do tend to get large. The one we studied there was with BRB as our force-limiting device, and again with rubber bearings between the shear wall and the floor system. And I'll show you a video of that, and a couple of videos actually. This is not necessarily so interesting. It shows that the BRB is kind of doing its thing. It's controlling the force that gets transferred from the floor system into the shear wall. And the next video shows the rubber bearings doing what they have to do. It shows that we actually push them through a pretty large deformation. This is the top of the shear wall, and that's the floor system right above. And we see that the rubber bearing is actually has to deform quite a bit in the way we've designed it. So here's some numerical results, which give us an idea of some of the requirements here. We have a gravity load system in this numerical model. Over here, it's basically a simple frame. We have a shear wall, and we have these deformable connections between them. And in this initial study, we had very simple models, a stiffness, a secondary stiffness, and a capacity FL. And we studied this under, I think, a set of about 18 ground motions, if I remember correctly, something like that, of say 20-odd ground motions. We initially did a very large parameter study where we varied the force capacity by a factor of 10, and we varied the stiffness by a factor of 100, and varied the secondary stiffness from 0 to 5%. And that's what's shown here. We also had in here a rigid elastic case, which is shown way up here just to get it sort of in the high strength, high stiffness case. And that would be like a conventional system. And so here's some results to show you how effective this thing is at reducing the force which gets transferred into the structure. So here's a sort of typical mean value of the results. We used two different kinds of connections here. One was a friction device, one was a BRB. It doesn't matter too much. So that's sort of the mean value. And here's the force being transferred from the floor into the shear wall at every floor. And there's the mean value for the rigid elastic case. And you notice that the mean difference is quite significant, but also there's a tremendous dispersion in the force being transferred in at each floor for the various ground motions, whereas for the force limiting case, obviously it's being controlled by the strength of the connection. And here's the story shears. There's the mean value with the force limiting connections, and there's the mean value for the case with a rigid connection. And really want to, I guess, focus our attention in this case on the base shear in the shear wall. There's the dispersion or distribution of results for the base shear for the rigid elastic case for a conventional system, and here it is with our force limiting connection. This is about a 45% reduction in the mean value of the base shear, and an 85% reduction in the dispersion. So now what we've done with this thing is essentially eliminated the uncertainty in how much base shear you need to design for, as well as control it. And effectively, we eliminate the uncertainty in the base shear because we've eliminated the higher mode response, which was really sort of our goal here. Okay. As far as the consequences of this, we have to, of course, accommodate that deformation. And here we see about 40 millimeters of deformation, typically over the height of the structure, which is not excessive, really, to get that kind of result. And we don't really see any significant increase in the drift of the gravity load system, which would be other concern, is if we're letting the gravity load system deform a lot more, then we're going to create other problems with that system, with that result. So we don't really see that significant difference. Some variations in specific stories, but not overly so much difference. So this is also still a work in progress. The experiments we have conducted already in the past show that we can make this thing work, it can be designed and constructed and perform more or less as expected. We limit the forces transferred from the floor system to the lateral force resisting system, which reduces the floor accelerations and the story shears in the lateral force resisting system. I think more importantly that we really control the dispersion, which means you have a much more reliable result in terms of what you're designing for. And you can find that paper here in the proceedings from last year at the New Zealand Society of Earthquake Engineering annual meeting. And also there's a kind of advanced version of a better paper, I think, in earthquake engineering and structural dynamics. So here's the conclusions from the whole thing. And what I told Quincy earlier today is I enjoyed trying to knit together results from like 4 or 5 PhDs, which really was an interesting challenge for me because I wanted to talk about higher mode response, and I had different people studying it in different ways, and here was a chance to try to pull it together, perhaps not as successfully as I would have hoped, but hopefully close. The first thing is that these self-centering systems have the potential to survive these earthquakes, either DB or MCE possibly, without significant structural damage, which at first is a pretty impressive potential. The rocking response is a first mode response, but it also, by controlling the capacity, you can control the first mode response. And I don't think that's anything new. That's just a summary of what we learned a while back, a long while back. But if you really want to get that kind of potential, you really have to figure out what to do with these higher modes. To get that damage-free response, you're going to have to figure out what to do with these higher mode forces. They showed actually showed 3 ways. One way is just to design for elastic response, which means you have to design for pretty large forces, which have a low probability. You could include a second mechanism to control a second mode response, but then you see the third mode is still there facing you. Or you could use these deformable connections to limit basically all the forces that get transferred in and really control the higher mode force response directly. So that's it for the talk, and I really appreciate your attention and the opportunity to be here, so thanks a lot.